Problem 65, back to probability. I think what you'll see in this problem is that it's a fairly straightforward application of Bayes' theorem. Bayes' theorem is a statement on conditional probability. It tells you that the probability of A given B is always equal to the probability of B given A times the probability of A divided by the probability of B. And as long as you have that memorized, this problem's not too hard to do. And I'll solve it this way in just a minute. But I prefer not to use Bayes' theorem on problems like this. I think there's a much more intuitive way to do it. So what's going on in this problem is I have a population of men, and 5% of them have a coronary artery disease. I have this diagnostic test that's sometimes correct and sometimes it's not correct. If I give it to someone who has the disease, it's correct 24% of the time. If I give it to someone who does not have the disease, it's correct 98% of the time. So I got false positives and false negatives. If I randomly choose a man from the population and the test says he has the disease, then what's the probability that the test was correct, that he does in fact have the disease? Well, what I like to do is, since there's two different percentages, let's just pretend that we have 10,000 men, right? 10,000 being 100 times 100. So I got these 10,000 men and I know that 5% of them have this disease. So if I only had 100, 5% would be 5. So 5% of 10,000 would be that 5 with 2 more zeros. 500 of these men have the disease. Since 5% have the disease, 95% don't have the disease. 95% of 10,000, you can probably just figure that out, but the way I think about it is 95% of 100 is 95, and then I have these extra 2 zeros. For the men that have the disease, the test is right 24% of the time. So if I had 100 men, 24% would be 24, but I have 500 men, so I need 5 times 24. In other words, 120 men over here. 120 of these 500 men went over here, so the remaining 380 must be over here. Of the 9,500 that have the disease, it looks like I wrote have disease, have disease. Sorry, I meant to write don't have the disease over here. Anyways, for these 9,500 that don't have the disease, the test is going to be correct 98% of the time. That means the test is going to be incorrect 2% of the time. If I only had 100 men, 2% would be 2 of the men, but I have 9,500 men, so 2% is 2 times 95, in other words, 190. If the test was incorrect for 190 of these men, then the test would be correct for 9,500 minus 190. What's that, 9310, I guess? I've taken the 10,000 men and I put them into these 4 different buckets. With this flowchart, answering the question is simple. If a man is randomly chosen from the population and the test indicates that he has the disease, so that's someone who had the disease and the test was correct, or does not have the disease and the test was incorrect, it's one of the men that end up over here or over here. We want to figure out what is the probability that the test was correct. Well, for these 310 men, 120 of them, the test was correct. The probability would just be 120 divided by 120 plus 190. In other words, 120 over 310. In other words, 12 over 31, which is what, 36 over 93, which is a little bit more than 36%. It looks like it's roughly 39%. The answer to the question is just E. I personally find it a lot easier to do this little flowchart and figure out the probability by adding up some numbers than using Bayes' theorem. But if you really like Bayes' theorem, you can do it that way as well. So what the question comes down to, if the test indicates the person has the disease, so given that they test positive, then what we want to find is the probability that the test was correct. So if they test positive, saying the test is correct is saying they have the disease. So find the probability that they have the disease given that they test positive. In the language of Bayes' theorem, A is have the disease and B is test positive. So the probability of A given B, the probability that they have the disease given that they test positive, is equal to the probability of B given A, the probability that they test positive given that they have the disease, times the probability of A, the probability that they have the disease, divided by the probability that they test positive. If we can figure out these 3 probabilities, all we gotta do is multiply and divide and we're done with the problem. So what's the probability that they test positive given that they have the disease? Well, it says right here that for men who have the disease, the test is correct 24% of the time. A correct test, if you have the disease, would mean that you tested positive. This probability is 24%. What's the probability that they have the disease? That's given right at the start here. 5% of men have the disease, so that probability is just 5%. And then finally, what's the probability that they test positive? Well, that one's a little bit trickier. If you have the disease, which remember is only 5% of men, then you're going to test positive 24% of the time. But if you don't have the disease, which is 95% of men, you're still going to test positive if the test is incorrect, which happens 2% of the time. So the overall probability that you test positive is this sum here. Since we don't have a calculator, it might be easier to compute this if we multiply the top and the bottom by 10,000 to get rid of all the decimals. That would leave us with 24 times 5, in other words, 120 up on the top, 24 times 5 here, another 120, and 95 times 2, in other words, 190 here. As we've already seen, the sum of 120 and 190 is 310. So this probability is 120 divided by 310, which we ballparked earlier to be about 39%. Maybe a better way to ballpark it would be divide the top and the bottom by 3, and we get that that's 40 divided by about 103. So really close to 39%. 39%, as we saw earlier, is answer E, the answer to the question. Essentially, using Bayes' theorem is identical to using this flowchart. I just think it's quicker to use the flowchart and less likely that you'll incorrectly identify what A and B are in this formula and accidentally put the wrong numbers in here. But I don't know, maybe that's just personal preference.